we're going to determine whether a given set of ordered pairs reflects an exponential function or not, and what that pattern should give us in order to determine if the function is exponential. Well, for example, here, if we looked at the average rate of change from one point to another, it would be the change in y over the change in x. And so if we took a look here, the change in y from this point to this point is 3, and the change in x from this point to this point, let's see, that would be 7 minus 4 gave me 3, and 0 minus a minus 1 would give me 1. This is a 3 to 1 change in y over change in x, and so my average rate of change from this point to this point is 3 to 1. And if I went and checked it out again, maybe I'll use an arrow here, it might be a little easier to fit in all my data. I'm going to go ahead and do 10 minus 7. Now remember, when you find a slope or an average rate of change, you always have to go in the same order from point to point. So if I do 10 minus 7, which is 3, then I have to do 1 minus 0, which is 1. And it looks like I'm getting back that same average rate of change of 3 to 1. And I think if I continued on down here, this would be 13 minus 10 is 3, over 2 minus 1 is 1, and that's a 3 to 1. And I think this final is also a 3 to 1. 16 minus 13 is 3, over 3 minus 2. And when the average rate of change is constant, then you don't have an exponential function. That is just in this case, that's a linear function, right? 3 to 1 again. And so when the average rate of change is constant, my average rate of change is constant. So I have a linear function. The relationship from point to point is a constant rate of change, and therefore I have a linear function. So this one was not an exponential. Okay, and so when I get my choices here, it looks like I just say it's not exponential. Right? Okay, but when I go ahead over here and I go ahead and give this problem a try, let's see how I determine this one will turn out to be exponential. So let's first determine the average rate of change, just like we did from point to point. And let's see what happens here. Now, if it is exponential, the average rate of change should not be constant. It's only when your slope is a constant rate of change that you have a straight line. But let's see what happens here. So the average rate of change is found the same way we just did up above. Okay, so the average rate of change here would be what? Well, if I do 1 minus 6/5, 1 minus 6/5 for the numerator, over 0 minus a minus 1, I'm going to go ahead and have a negative 1/5 over 1, or a rate of change of negative 1/5. Then if I went and I took this one right here, right, that would be 5/6 minus 1 over 1 minus 0. And that is going to be a what? Well, 5/6 minus 6/6, which is equal to 1, is 5/6 minus 6/6 is a negative 1/6 to 1. And that's not the same. Negative 1/6 to 1 is just negative 1/6. And I am not getting, it looks like I'm not getting constant rate of change. Now that, just because it's not constant doesn't make it exponential. All we know so far is it's not linear. But let's keep going. Let's compare these two sets of points, right? So in this particular case, 25/36 minus 5/6 would be my numerator, all over 2 minus 1, which is just simply 1 again. And by the way, what would happen here is, this is really, if I multiplied this right here, 6 on the top and 6 on the bottom, I'd get a common denominator of 36. This would be 25 36 minus 30 36. And I would get now negative 5 36 over 1, which is just negative 5 36. Okay. Now I'll tell you what, I'm not going to go ahead and do the next one. This particular problem has lots of fractions in it. I think this would be enough. Let's go ahead and take a look at why we know that this would be exponential, that this particular function is coming from this particular set of ordered pairs is coming from an exponential function called h of x. Well, while our average rate of change was not constant, we do have a situation that is constant. It is called the ratio of outputs. So let's look at the ratio of outputs, right? So here are our outputs. And let's take a look at the ratio of outputs, right? Well, if we did a ratio of outputs, of consecutive outputs here, I should say consecutive outputs. Let's see what happens. If I formed the ratio of 1 over 6/5, that would be the ratio of these two consecutive outputs to our function, and I would get 1 over 6/5. And remember, to divide by a fraction is to multiply by the reciprocal. This would be a ratio of 5 to 6. Let's see what happens the next time. Let's take, that was 1 over 6/5. Let's take 5/6 over 1. Well, when you take 5/6 over 1, that already is 5/6. Oh, okay, well, look we're starting to get a pattern here. We're getting a constant, not a constant average rate of change, not a constant slope, but a constant ratio of outputs. And when that happens, then you know that you have an exponential function. Let's try it on the next one. This would be the ratio of what? 25 over 36 to 5/6. And let's see how that one would work out. We'd have 25 over 36 over 5/6. Then to divide by a fraction is to multiply by the reciprocal. By 6 over 5. This would cancel, we'd get 5. And this would cancel and we'd get 6. And once again, the ratio of consecutive outputs is turning out to be 5/6 every time. And when you have a constant ratio of consecutive outputs, then that means you have an exponential function that is producing that phenomenon of having a constant rate of a constant ratio of consecutive outputs. Okay, right? And so let's just take a look here. Let's think about this a little bit. I mean, now I'm not going to expect you to do this on a lot of problems, but let's just see if we could come up with a function, and it's going to be exponential, that if we raise a certain quantity to a power, and these would be the powers right here, -1, 0, 1, 2, and 3. Let's see if we could get it to produce these outputs. Well, I think that when x was 1, okay, that's going to help me here, because I think if I get 5/6 for an output, I have a feeling that what we have as a function is this: 5/6 raised to the x power might very well be our function, because when x was 1, I got 5/6 for an output, right? For example, h of 1 would be this. But let's test it on some other values. Let's see if we're right. Okay, let's try putting 2 in there, for example. So what would h of 2 look like if h of x was 5/6 raised to the x power? H of 2 would be this, 5/6 raised to the second power, and that does turn out to be 5 squared, 25, 6 squared, 36. And it looks like we're on to something here, right? That seems to be the function. Let's try it again. In fact, let's try with the third power. So we got h of 3 would be 5/6 raised to the third power, and 5 cubed is 125, and 6 raised to the third power is 216 if we try that in our calculator. So our answer here, the a value, if you're talking about a general form of an exponential function, is 5/6. And I think we have an exponential with 5/6. I think our answer here is this right here, C. Right? Our general function is 5/6 raised to the x power. And you can see what's happening is every time we raise it to a power, we're multiplying by an additional 5/6. And that is producing this pattern right here.